Good morning, everyone. It's a pleasure and an honor to be here today. So, quick introduction about myself. I am Jēkabs Priedītis, a bachelor's level student of physics at the University of Latvia. I also work as a physics teacher at the Rīgas Natālijas Daudziņas Vidusskola, and I'm also an aspiring researcher working at the Numerical Modeling Institute of University of Latvia. And what I'd like to share with you all today is the research that I've done at the Institute with my colleagues for the past year or so. Mostly all of us still undergrad students. We've been working on assessing the potential for autonomous infrastructure. Infrastructure that works purely on the basis of wind power and solar power with the assistance of battery storage. We're focusing mostly on communication towers in particular, though any infrastructure, these principles would apply to any sort of infrastructure. So given this topic's connection and relevance to this seminar, I hope that some of our findings are of some value, or at least spark some thoughts. So without further ado, quickly the sort of structure of this presentation. I'd firstly like to speak on the objectives of this project, then the importance for coastal and offshore applications, then most importantly, the results, and finish off with conclusions and further areas of research, the plans for the future. So the primary aims of this project are as follows. Firstly, during the first stages of the project, the initial goal was assessing whether such infrastructure is even feasible in the first place. If it was found to be either technically too impractical or too expensive or too unreliable, then I would probably not be here today. So assessing the potential and the feasibility was the first important goal. After that, the next was mapping the potential of such infrastructure across all of Latvia, and in later stages across all of Baltics, in order to find the most suitable places for the development of such infrastructure. Because even with such a relatively small area as the Baltics are, the differences can be quite significant, not just comparing the coastal and offshore regions to the inland ones, but also within these categories. This is also a time to admit that most of the research was primarily done for inland applications at first, as the prototype for the power is located inland. However, for the purposes of this presentation, I'll try as much as possible to bring an offshore and coastal perspective to all of this. So once we had a clear indication that all of these towers are feasible, the next step was to look at ways to optimize them. So if you want the system to be as effective as possible, then we would have to look at, for example, what kind of combination of solar, wind, and battery would give the most efficient and the most cost-effective outcome. What the differences for this most optimal system would be across various places in the Baltics. How large should the battery bank be, and just a flurry of similar questions that have to be answered in terms of optimization. Another important part of the project was identifying the shortcomings, the various periods of outages, when they occur, how long they are, how severe they can be, and even if the outages are relatively rare, then understanding the exact conditions under which these outages happen is crucial for improving the systems and also showing what kinds of applications it can support, which leads to my next aim, determining what power usage profiles could such systems be useful for, and hence what applications could sensibly be run on them. Of course, we're talking about relatively low to medium power infrastructure. We're not talking about off-grid factories or data centers or anything like that. Mostly medium power infrastructure such as communication towers, monitoring equipment, certain categories of measurement devices, and similar distributed systems for which such setup could be practical. And finally, it's also worth mentioning that this is not merely a hypothetical project, so not something that is merely from the passion of some students. All the calculations, the modeling, and the configurations have actually been used to build a functioning tower in real life, which means that all of this analysis has also practical grounding, not just theoretical. And although the tower is set to run, have the wind turbine spinning and the solar panels working only within the next month or so, it has been built in real life so far. So moving on, for the importance in particular for the offshore and coastal applications. These regions, I'm sure all of you know better than I do, come with their own sets of difficulties. Infrastructure in these regions is quite sparse. Grid access can be limited or non-existent, and weather conditions are harsh enough that any system of this sort not only has to be self-sufficient in terms of energy, but also be physically robust. And the further from land you go, the more difficult everything becomes. There is also the less pleasant, but unfortunately unavoidable factor that, given the current political landscape being as turbulent as it is, the importance of a two-layer safety net is more important than ever. Unfortunately, this is no longer some theoretical, hypothetical doomsday scenario, but rather this deliberate interference, jamming, GPS spoofing, and other forms of electronic interference are real risks, and the Baltic Sea in particular has seen plenty of such activity, which highlights the increased need for such infrastructure. So the results section, I'll organize it by starting off talking about the inland point, the one that we have already built, then move on to a more broad perspective across all of Latvia, and then focus on a coastal point. So this inland point is located in the central southern part of Latvia, near the city of Dobele. For a very important piece of context about the further slides and calculations that are done, this current tower configuration contains a 5 kilowatt turbine at a height of 56 meters, solar panels with a total power of 18 kilowatts, and batteries at a total capacity of 25.6 kilowatt hours, which of course doesn't mean much if we don't know the power consumption. The most important part to scale it against is the power consumption, which we found that of these sorts of communication towers, we used an analogous one in a similar location. We found the average to be 2.1 kilowatts, slightly more during winter and slightly less during the summer. And using 30-year data from the New European Wind Atlas, as well as ERA 5, and simulating a battery which every hour takes a certain amount of energy from the solar powers and turbines, and uses up a certain amount of energy from this power consumption. We modeled the way that this tower works. So finally getting into the real results, one of the beautiful things about a hybrid energy system is the fact that during the months in which the solar power generation is relatively lower, the winter months, the wind power is slightly higher, which helps significantly to ensure the autonomy of such infrastructure year-round. It is important to mention that during the winter months, the generation is still lower. The wind during these months is not as high as the solar power during the summer, though especially with us placing the solar panels at an angle which is most efficient, in particular for the winter months, at a 60-degree angle. the situation is made to be slightly better for autonomy in the winter months as well. When modeling the outage percentages for this current configuration in this inland point of the tower, we found that the average across the entire year would be roughly 6%, essentially non-existent during the summer months. However, the real problematic areas would be the winter months, in which it ranges anywhere from 15 to 18 to 19% during these months. Which is, of course, not the most ideal outage percentage. This is something that would certainly have to be improved, and therefore we also ran an optimization algorithm to find the most ideal, the most cost, and therefore we also ran a 99% uptime for this inland point, and we found that for this power consumption profile with an average of 2.1 kilowatts, ideally, most efficiently, we would use solar power of roughly 37 kilowatts. Wind power would not change so much. A 6 kilowatt turbine would do the job, and a battery capacity of 54 kilowatt hours would be sufficient. And when it comes to cost, we also calculated the cost using the current energy system, current panels, inverter, turbine, and batteries used in the project, which were deemed the best by our project partners. And we found that the cost of these power systems, not including the labor to set it all up, and also not including various minor installation components, at an inland point such as this would be roughly 45,000 euros. Of course, that's by all means significant money, but it's also important to note that renewable energy systems are decreasing in price in time, and also given that something like this is very low maintenance and can potentially run even for a couple of decades, this is, I believe, to be quite a worthwhile product. And the wonderful part about it all is that this is for an inland point, quite deep into Latvia, for a more windy area, and for an area with a slightly higher solar potential as well, such as this beautiful city of Ventspils or any coastal region. The results are even much better, as we had mapped during the early stages of the project. The coastal and the offshore area has I'd say roughly 1 to 1.5 times more to 2 times more total power generation potential than, for example, a point that is deeper inland, than, for example, the valleys of Gauja, the river Gauja, which were found to be of much lower potential. Therefore, this sort of infrastructure could be particularly strong in the coastal and offshore areas. When we had mapped the outage percentage using, again, the same system that we're using in the inland location, using the same power consumption profile, we found that in the coastal and offshore regions, the power outage would be of this system would be 2.5 to 4% compared to, again, locations that are deeper inland, which reach up to 10%, up to a 10% outage percentage, which further shows how much better such systems could work near the sea. So finally, moving on for results at a coastal point, I chose a point at the very coast, roughly between Ventspils and Liepāja, near Pādilos, in the center of this western part of Latvia. We found that the average power outage time is more than 2 times lower. Again, we have the same problem that during the winter months it is higher. However, in total throughout the year, it would be only about 2.6%. And also, again, trying to find the most efficient setup that reaches a 99% uptime. The needs and the cost would also be much lower. Solar power would merely have to be about 25 kilowatts. Wind power is roughly the same. These same 5 to 6 kilowatts would do, and a battery capacity of 47 kilowatt hours, which would create a total cost, a significantly lower total cost and just a slightly higher cost than at this current location of 38,000. And such a trend of the price being much lower is visible all throughout Latvia. This project is still currently ongoing, so we're working on adding more points and adding a proper interpolation throughout all of it. However, in a map like this, with the points that we have, it is very visible that at a coastal, at an offshore, at an offshore point, this system would be much cheaper and work better. So to conclude, I think the most important takeaway is the fact that the idea of an autonomous renewably powered communication tower or anything of a similar power consumption profile is not only technically feasible, but also genuinely promising for the future. And even with its limitations, even with a limited size turbine at a limited height and then undersized battery bank, the system works decently well. And if we found that the system works decently well at the inland point in slightly, I guess you could say suboptimal, at a suboptimal location, we can infer that the system would work even better at a coastal point, for example. Which brings me also to the second major conclusion that location matters more than anything else. The difference between central Latvia and the western coast is quite enormous. Coastal regions benefit very significantly from a higher wind potential, which in turn drastically decreases total outage times and the total cost for ensuring these low outage times. And the third and maybe slightly less important conclusion is that autonomous powers of this sort are incredibly important, especially with our current geopolitical situation, due to this signal interference being increasingly common. Therefore, improving resilience in these coastal and offshore regions is crucial. And as for future research, there are several ways forward. The most important one would be that after this tower is fully set up, after the turbines starts running and the power starts being generated, we would have to compare these real life data to our simulations. It's one thing that everything works well in our computer, but validating all this data against the actual model, real weather, real power systems, and the real hardware quirks that always come with this sort of project will certainly help refine the methodology and make the system better and more robust. Another direction would be expanding this research for infrastructure of different consumption profiles. Communication towers, which we focused on, are just one example. However, as I previously mentioned, any monitoring stations, navigational beacons, offshore sensors, coastal radar equipment, and other similar sorts of low to medium power infrastructure all have different energy needs, and quantifying exactly what those needs are and at what times and what is the most optimal way of ensuring the proper working of all this infrastructure is something that I think would be extremely valuable. And there's also room to explore, let's say, more advanced forms of optimization, making sure that the system works well also for near future weather forecasts, also integrating small scale backup systems such as hydrogen storage. That was another point of research during this entire project. And of course, also extending this model across the entire Baltic region, and even to the island territories as well. It would also give a broader understanding of where these systems could have the most potential and where they could be the most impactful. So thank you very much for your attention. There's
That's it. Sorry, that was the color. When I signed up the graphs, I will looks like for record something called that. Then we just be carried away.
Unfortunately.
Well, I think that's one of the most mistakes. Kind of absolutely, and here's the part that really actually.
I'll work on it, I promise. It's coming.
Actually, so it's coming to my side. So we are in Latvia University and Latvia International Research Center. And one of our activities is study of black holes. They're like the most darkest objects in the world, in the universe. And actually, so maybe it's not now, but in part of future, it's an enormous and enormous source. It will be used in very compact as well. But it's probably not in 100 years or maybe even more, but it's part of future. Thanks again. And there are some questions from my side. This solar panels, 25 kilowatts, how big are it? 25 kilometers.
Sorry, the area? That is, for context, you could think that one of these solar panels, which were used for the project, is 450 watts. Therefore, it would be roughly 50 of these panels. How large panel is so
50 square acres. It's very yep, so good. So
it is certainly a significant area.
Yeah, and it's again a nice result of closed areas is most promising for putting autonomous systems. But probably if you go far away from a source, that it's additional expenses for deploying towers and so on. Also on a platform, so something like
for sure, yeah.
We have additional price. But it's probably not need some big towers and not so big solar panels here. Yeah, thanks a lot. And yes, definitely we're experimenting with by products that what's it like for I could put the
in the project we found that the typical the typical axis I'm currently forgetting, I think it's the horizontal one now, which is used for most wind turbines, was also the best one for this application.
Yeah, thanks a lot. There you go. About you. Another look at it too. Is able because it only comes.
That would be another potential line of research. During this project, we have not done any research on that. However, that certainly has a lot of potential, and that would have to be looked at.
But actually, in my presentation about the linear generators, I have a couple of slides about the rate turbines. So I will explain it now. Okay, so yes. So thank you for coming, and you also thank you so much for your talk. Thank you.